Okay, so for this afternoon, we'll really be going to start with the introduction to first order, rather the introduction itself to differential equations, because we're not able to start with that. So I will share Canvas with you. By the way, class, so I will share now my screen. And this is actually your syllabus in Canvas. So please read the syllabus so more or less you would know the coverage. Anyway, I have shown it to you already using a different course style. So now for this afternoon, I go to modules. And we'll go to the first part, which is the introductory concept. So I'll click on this. This is the same thing that you'll be also seeing. So it's not published. So I'm going to publish everything. Okay, module 2 is published. Now we go to lesson 1. Okay, please let me know through a thumbs up sign if you could see the introductory concept and principle page in your course style. Okay, thank you for that. Thank you. So now we will be discussing about what is differential equations and the primary fundamental things and concept you need to know about it. Okay, now when we speak of a differential equation, this is an equation of an unknown function and its derivatives. If I will simplify the definition, we say it's a differential equation if it contains a derivative or derivatives of an unknown function. Now, some equations may not have the presence of derivative or derivatives, but it has the presence of differentials. So differentials, once already expressed in terms of another, can now be viewed as a derivative. So that then can still make this equation what we call a differential equation. So let me annotate. So when we speak of a derivative, we mean, let's say, for example, the common one that you know is dy dx. Or it could be a dv dt. Or the way we write in shortcut derivatives like this, a third order derivative. So these are derivatives. When you speak of differentials, you may only have a dy or a dx or a dt. So if your equation does not contain a derivative or derivatives, but it has the presence of two differentials, which could be expressed in terms of another, like this one, the differential of y in terms expressed in terms of another differential dx, then now we can view this as a derivative. If again the equation does not contain the derivative, but it has two differentials, it's still a differential equation because we can have our equation divided by one differential and you already have the presence of a derivative. So simply put, when we speak of a differential equation, it's an equation which has the presence of a derivative. Now, in terms of the types of DE, we have two. Excuse me, guys. I'll just increase the percentage. It would be bigger. So we have two. So one is ordinary differential equation. So in here, your dependent variable depends on only one independent variable. So involves ordinary derivatives only. So an example would be like, again, I like to annotate. So ordinary differential equation will have a dy dx plus 2y equal to 10 ln of x. So this is a differential equation. You have one independent variable. We call the variable below the derivative as the independent variable. And we have what we call as the dependent variable, or referred to also in other textbooks, the unknown function. So if your differential equation contains only one independent variable, then it's an ordinary differential equation. But in terms of form class, it's so easy to look at what an ordinary differential equation is. So whenever you see only a D, You see this D here? That makes the derivative ordinary, the D in here. Now, otherwise, if you see this curly D, which you have encountered in your differential calculus, then it's a partial differential equation. So an example, I can write here an example. So you can have, let's say, for example, the partial derivative of, or the second partial derivative of V with respect to S and with respect to T, plus the partial derivative of V with respect to, let's say, R, equal to 0. This is so easy to say that this is a partial differential equation primarily because of the symbol that was used. We call this the curly D symbol. Okay, so this one is the second partial derivative of the dependent variable, the unknown function. First with respect to S, then second differentiation is with respect to T. Whereas the first term in here, or the second term, is already your unknown function having its partial derivative expressed in terms of R. So in here, your independent variable, in this case, I like to use a different color. Your independent variable in this case now would be 3. You have S, you have T, and you have R. Why? These are the variables that you see written below your partial derivative. So whenever your differential equation has more than one independent variable, we say the differential equation is a partial differential equation. But still, class, look at it. It still has one dependent variable, or what we call the unknown function. Whereas an ordinary differential equation has only one and only one independent variable. Still, just like the partial DE has only one unknown function or dependent variable. But as I've said, even if you don't know yet the concept of the independent variable and the dependent variable, it's so easy to spot which one is ordinary and which one is not based on the symbol that is being used. So the D for the ordinary derivative, the curly D for the partial derivative. So let me clear the drawings. Now, when an equation involves one or more derivatives with respect to a particular variable, that variable is called the independent variable, the variable that appears in the denominator of your derivative. A variable is called dependent, or in other texts, it's referred to as the unknown function, if the derivative of that particular variable occurs. Meaning, it's the variable that appears in the numerator of your derivative. So those that are not variables, meaning letters that does not appear in your derivative, but could be seen in any of the terms in your differential equations, those are what we call parameters or constants. They are not to be viewed as variables. The variables are only those that appear in the derivative or that appears in the partial derivative. Okay, so as an example, like to make this bigger again, a little bit bigger. So in here, I have a table as to the type of the ordinary differential equation, the independent variable, the dependent variable, and the parameters. So in here, you have, for this first example, you have an ordinary differential equation or an ODE. In here, it's another ODE. This one is a partial differential equation, a PDE. And the same thing with this. It's a PDE. Partial because of the symbol that appears in the differential equation itself. As to the independent variables, these are the variable that appears in the denominator of your derivative. So let me just annotate because there's some mistake here in the first row. Okay. Now, the independent variable class in the case of the first DE here should be, this should be X. And the dependent variable should be Y. Your parameter, the other letter that appears in your DE but is not written on the derivative is K. Okay? Now, for this one, for the second example, Your independent variable is t. That is correct because that's the variable that appears in the denominator of your derivative. And your unknown function is I. So you have here I, and I. The other letters that you see, the L, the R, and the C, together with the E and the omega, are what we call parameters. They are not variables because, again, as I've said, the variables are the ones or the letters that you see on the derivative or derivatives of your DE. For this one, these two, the last examples, which are both partial differential equations. So in the case of the independent variables, so we have now more than one. In the case of the first example, you have x and y. And your unknown function is v. As to a parameter or parameters, there's none. I don't see any letter here except v, x, and y. So there's none. Now in here on the second and the last example, second partial DE, your independent variable is still x and y. Your unknown function or your dependent variable is f. You can see that's an f. And your parameter is n because there's a letter here that is written that is not appearing on the derivative itself. So what's only appearing in the derivative is the f and x and y. So other letters that you see in your DE will be viewed as constants or parameters. So in this case, your parameter is n. Okay, so that's the very simple illustration of the independent variables, the dependent variable, the type of the differential equation, and the parameter. Now let's go to determining the order and the degree of a particular differential equation. So the order of the DE is the order of the highest order derivative appearing in the equation. The degree of the DE is the power to which the highest order derivative is raised. So meaning, before we can know the degree of the DE, we first need to determine which of the derivatives that appear in your differential equation is the highest ordered. Whatever is the exponent of that, that would be the degree of your differential equation. And speaking of degree, class, when we speak of a linear differential equation, it's a differential equation of degree 1. Or shall I say specifically, all the derivatives in that particular differential equations are raised to 1. If that is the case, your differential equation is said to be linear. So no derivative should be raised to an exponent other than 1. So all your derivatives should be having exponent equal to 1. So let's go through the examples that I placed in here. So dy dx equal to 5x plus 6. So it's of order 1 because this is your only derivative. And this is a first order derivative and first degree, because this one is understood to be raised to 1. By the way, class, this is also a linear differential equation because the exponent of the derivative is equal to 1. As to the second example that we have here, this is of order 2. Order 2 because this is the highest order derivative. This is first degree or degree 1 because the exponent of this is equal to 1. Now, this is also linear because the derivatives here are all raised to 1. So this is a linear differential equation. Now, as to our third example, this is a third order differential equation and is also first degree. This is also linear. This one is a first order differential equation. This is a first order derivative, but this time second degree because the exponent of your derivative here is 2. But this is non-linear already, primarily because of the 2 here as the exponent of your derivative. Now, second to the last example, you have here a second order derivative and a first order derivative. So which of the two is higher in order? This would be it. So the order of your DE is second order and the degree is 7. you don't use the 20 because the 20 is the exponent of the first order derivative. And it is not the highest order derivative that appears in your DE. So the exponent of the highest order derivative should be the basis of the degree of your differential equation. Just like this one, this is non-linear. This one is also a third order differential equation, second degree, just like the first here. The first differential equation, which is second degree, non-linear. This is also non-linear, primarily because of the exponent of this third ordered derivative. So it's so easy really to tell the order and the degree of your differential equation. Any questions so far? Okay, so there's none. So we go to solutions of differential equations. Class, what is so unique about differential equations is that one particular differential equation may have three different forms in each solution. So meaning a differential equation that is given to you may have what we call a particular solution, a general solution, or what we call a complete solution. So all of the solution representation for your differential equation are acceptable, and any would be also acceptable as long as it gives you the solution of your given differential equation based on the provided conditions, if there are conditions. If there are no conditions, then the solution that will be arrived at, or the solution that you will be getting, will be either a general solution or a complete solution. Now let's distinguish one of these three from each other. So we will distinguish one from the other. So when we speak of a particular solution, this is any solution, but take note, I'd like to annotate this one. This particular solution of your differential equation does not have an arbitrary constant. So take note of this. No arbitrary constant. Wala arbitrary constant. The general solution is the set of all solutions, or a set of all solutions of your DE. And the very important thing that you are to take note, class, in here is it has at least one arbitrary constant. So take note, the other one has no arbitrary constant. This one has at least one arbitrary constant. What about the complete? So from the term itself, complete solution, this represents already the sum of the particular and the general solution. So if I take the sum of the particular solution and general solution of a differential equation, that would be its complete solution. But there is one thing worth noting here about the complete solution, and this is really what you're going to remember, and I'd like to emphasize this. The number of arbitrary constants here in this solution is equal to the order of the differential equation. So meaning, if you have a second order differential equation, the number of arbitrary constants should be 2. That way your solution can be classified as a complete solution. This particular complete solution, which has the 2 arbitrary constants for your second order DE, is also known as the general solution. Now you may wonder, why is it also known as the general solution? Because it says here, class, that the general solution has at least one arbitrary constant. So if a solution of your differential equation contains an arbitrary constant, automatically it's already a general solution. If the number of arbitrary constant is equal to the order of your DE, then it's now what we call a complete solution. So we can say that all complete solutions are general solution, but not all general solution complete solution of your particular differential equation. The particular solution, on the other hand, class, does not have any arbitrary constant. Now, it would be easy for you to understand the concept of these three aside from the arbitrary constants that you will use as a basis by means of the following examples below. So I will scroll down, that way you will be able to see or distinguish one solution from the other. So since we have not yet learned how to find the solution of a differential equation, we will just go to proving, or let's shall say validating, that a particular solution is really the solution of a differential equation. And I will start with this number 1 example. Prove that y equal to -2 cosine 4x plus c is a solution to the dE dy dx equal to 8 sine of 4x. So you have to prove, that's the first thing. What is the solution of this initial value problem where y is equal to 6 and x is equal to 0? Now let me first explain what is initial value problem. A differential equation class like this one, dy dx equal to 8 sine 4x, is an initial value problem if it is provided with a condition. We call this a condition because it says here that when x is 0, y is equal to 6. This initial condition makes this particular differential equation an initial value problem. At the same time, this initial condition allows you to determine the arbitrary constant c of its solution. That way, from a complete solution or from a general solution, you will get what we call a particular solution. Now, we go first to the first statement. So it says you prove, so meaning you need to validate. So how do we validate? In here, class, the process that is illustrated here is already separation of variables. And I haven't yet discussed it. You can go back to the solution later when I am done already discussing separation of variables for first order differential equation. For now, I will simply use a mathematical tool that you have already learned in the past. That way, I will know that this particular equation here is really the solution of this particular differential equation. Now, I would like to ask somebody here if he or she has an idea of what particular tool you have learned already in the past will we use. That way, I can prove or validate that this is really a solution of this particular differential equation. What is that particular mathematical tool that you have learned already that we can use? That way, we can really prove that this one is a solution of this differential equation. You see here integration, but the integration here already class uses separation of variables, which I haven't yet discussed. So I'm asking for a different tool which will not yet use a technique that we will be discussing in the next few days. Anybody? How are we supposed to prove that this is a solution of this given differential equation? Anyone? Good. Okay, you can use your differential calculus. So what we'll do, I'll just lower it down so you could see. What we'll do, we will differentiate. I will differentiate the solution and check whether I'll get this one. So if I will differentiate this one, what I'll be getting is, okay, I'll be getting a dy dx. I'll be differentiating this in terms of x, so that's dy dx, and I'll also be differentiating this in terms of x. So I will have -2, derivative of cosine is sine 4x, and that would be negative. And then the derivative of 4x in terms of x is 4. The derivative of a constant c is 0. So now I have dy dx is equal to, this is negative, positive, and this is 2 times 4, that would be 8 sine of 4x. So what can you say? This dy dx, which is 8 sine 4x, is actually the differential equation that was given to you. So you were just simply asked whether this is really a solution of this differential equation. And it is, because it gave you the differential equation. Okay? Now you have already validated and proved that this is a solution of this particular differential equation. The next thing that you were tasked to do is you have to find the solution given that x is equal to 0 when y is equal to 6, or vice versa. Given that when x is equal to 0, y is equal to 6. What do you think is the purpose of this? I think I mentioned a while ago that the purpose of the initial condition is to find the value of the arbitrary constant c. This one, we need to find the value of the c. How do we find the value of the c? I think it's written there, but I will just write in here. So I'll use this condition that y is equal to 6. So I will substitute 6 for the y. So 6 is equal to negative 2 cosine of 4 times x is 0 plus c. So this is 6 being equal to a cosine of 0 is 1. So this is negative 2 plus c. So c then is equal to 8. Now, from this general solution, from this also complete solution of this particular differential equation, you have determined what we call the particular solution. Why is that? Because all you have to do is substitute 8 for the c here. So this will now be y equal to negative 2 cosine 4x plus 8. So this is now the particular solution. Well, this is a general solution, also a complete solution because your order here for the DE is 1. For order 1 DE, for it to be a complete solution, the number of arbitrary constants should be the same as the order, and we have it here as 1. Do you get it? I hope you now get the difference between the three forms of the solution of the differential equation. So the solution I illustrated to you for the second question is this. So this is now the particular solution of your differential equation. Now I will go down further. So this is the second example. Determine whether y of x equal to 2e raised to negative x plus x e raised to negative x is a solution of y double prime plus 2y prime plus y equal to 0. This time, class, you cannot anymore integrate because this one is a higher order differential equation. And this is a topic that we will still be discussing in the end term. So what will you do so that you will know that this is really a solution of this dA? So just like what I did in the first example, you simply differentiate, but this time you will differentiate twice. You need to find the first derivative. So the first derivative of this, I hope you know your differentiation. So this is the first derivative. I will not discuss it anymore because you're done with it. Now, this first derivative should be differentiated again to give the second derivative. And this is the second derivative. What do you do with these two? You substitute in the original dE. So your second derivative, you copy. So it was copied here. It's x e raised to negative x. Your first derivative is to be multiplied by 2. So you have twice of. So I copied the first derivative. What about the y that appears here? The y that appears here is in itself the solution that you need to prove whether it's really a solution of this given dE. So your y is 2e raised to negative x plus xe raised to negative x. Now, if this side is equal to 0, then we can say that this is really a solution of this differential equation. What form of the solution? This is a particular solution. Why? I don't seem to see any arbitrary constant. So this is a particular solution. So your algebra will let you know how to simplify this. And in the end, you will simply know that this is also 0, just like the right side here, which is 0. If you don't get a 0 here on the left side, then this one is not a solution of this given differential equation. Do you get it, class? Do you understand? Do you have any questions so far as to what I have discussed in here? Okay, let me stop sharing. Do you have any question? In terms of the introductory concept? No question? Okay, hopefully I'm right that your silence means that you understood everything that I discussed. So after this particular topic, let me just check. Okay, after this particular topic, class, is separable differential equations, or those that we call first order differential equations. So in the next days, in the next meeting, we will be discussing how to determine solutions of first order differential equations. Okay, now as to the the task that you will need to accomplish for this one, I will just change the dates there. I will update the canvas later tonight or early tomorrow morning. That way you will know what will happen next week. Of course, you will be given an assignment here. You have an assignment, and you will be given also a quiz on what I have discussed this afternoon. Okay, but it will be separate from the quiz for separable differential equations, which is the next topic, the first type of first order differential equations. Do you have any questions, class? Any question? No question? Okay, we have still 22 minutes. I'd like to proceed with separable differential equations. That way, if I am done with this, we will only have one makeup class to do. Okay? Just sit back there and listen. Anyway, you can listen again to the recording of this one with class. Okay. Okay, there's a question. No, none, miss. Thank you for that, Ruel. Okay. To share my screen for the separable differential equations. So you know already first order differential equations, you only get to see one derivative. And the first type that you will learn how to solve is the separable differential equations. So from the term itself, the variables can be separated. After it can be separated, you can now go straight to integration. Okay, I will go to the presentation of this PowerPoint. Okay, let me know if you cannot see the PowerPoint for first order differential equations. Otherwise, I will just assume that you can see the slide. Miss. Okay, thank you. So we go now to separable differential equations. If your differential equation, class, is written in this form, wherein you have the derivative here, and the rest of the functions consisting of the variables that you see in the derivative are written on the right side, or are written on the right side of your equation. This is a first order differential equation in form. Okay? It could also be something like this. I'd like to jump in here. In here, you have the specified derivative. In here, you don't have the specified derivative. So you have the m of x and y dx plus the n of x and y dy equal to 0. Instead of the derivative, what you have here are differentials. Okay, you see differentials. And we call this coefficients of your differentials. And these coefficients are either functions of x only, of y only, or a combination of x and y. Okay, I hope that is clear. Now let me annotate. If I will divide this differential equation by dx, by the differential of x, you will have this equation that you see on top. Why is that? If you divide by dx, this first term here, this dx will get to be cancelled, and you will be left with m of x and y. And your differential of y here, which is originally dy only, will now be written in the form of a derivative. So it's in the derivative of y with respect to x. Okay? So generally, I will say, class, that your differential equation, your first order differential equation, is separable if it has this form or this form. The goal in separable differential equation is you separate the functions in such a manner that the function, let's say for example, which has the x variable, is with the differential of x. The functions which has the y variable is with the differential of y. Why make it that way, miss? Why would you make it look like that? It's because after you have made sure that this is the form already of your differential equation, you can readily integrate. So all you have to do is use your integral calculus and you can integrate. And by the way, class, the form generally is not this one, but this. Okay? Most of the time, separable differential equations are not given in this form. It's a mix like this one or this one, which you need to make look like this. You have to make it look like this, which will make it readily integrable. That's it. We now are ready to determine the solution of a separable differential equation. Okay. It would be more clearer. It would be clearer if I will go to examples. Okay, so let's go to examples. You see this differential equation? This is the first form that was shown to you, like this one. Okay, we have the derivative and we have the function of x and y. So naturally, what will you do? Just simply separate. Let me annotate. So you transfer the dx in here. So you place it here by cross multiplication. This one, the quantity y squared minus 1, you place in here. So you have already y squared minus 1, differential of y. And this is the equation that you will be getting. Okay? And that's it, class. The purpose of separation of variables already yielded this expression, which you can right away integrate. So this is already integrable. This will only use power rule. This is power rule. This is also power rule. This is actually the solution of your DE. Now, as to the question where you're going to reflect the arbitrary constant C, I suggest that you always write it on the right side of your solution, because actually you have a C here. This is one integral, and you have another C here. But we will combine the two arbitrary constant into just one arbitrary constant reflected on the right side of your differential equation. This is, class, what we call as the implicit solution. Why I say implicit? Because you have not written it in the form y is equal to something like that. Okay? If you only have one variable in here, exponent raised to 1, and the rest of the expressions are written on the right side, that's what we call explicit solution. This one is implicit, but this is still solution. Okay, this is an acceptable solution. The reason why I'm going to share to you how to convert the implicit form of the solution to explicit is for you to not wonder later on when you are provided choices in the problems that you are solving. Why is it that your answer is not among the choices? Maybe the question is you have not written your answer in the explicit form, or you haven't simplified it. And that's the next goal of the next example. Okay? But before I go to the next example, do you have any question here? So what's done in here actually, transfer dx here. Transfer y squared minus 1 here. And this is the resulting expression. No questions?
Excuse me, miss.
Yes.
Ang sa simplification, lamis sa second to the last, miss.
This one?
Mag-times ka 3, miss. Ang C, hindi mo na pag-timesan, miss.
Okay. It's a good question. Your C is an arbitrary constant, right? The meaning arbitrary constant, it can be any constant that you have in mind. If you multiply it to 3, that would still be an arbitrary constant. So there's no need for you to write the 3. It's still another arbitrary constant. Okay? So you will see in books that you will be solving later on that the arbitrary constant multiplied to a specified constant is still another arbitrary constant. So you need not write the 3 anymore.
Okay, thank you, miss.
You're welcome. Any question? Okay, I cleared the drawing so we can proceed to the next. I think we'll be good with this because now will only be one meeting left behind my other classes. So we have here the concept of the implicit and explicit solution. So this is a form, again, the first form of separable DE. Let me annotate. Then we will still do the cross multiplication. I'll transfer this one in here. This one in here. So this is the expression that you will be getting. You do power rule for this one. In evaluating the integral, you do also power rule in here. So this is your answer. This is an implicit solution. How do I turn an implicit solution to explicit? Okay. I will proceed to the next page because that's where it's going to be presented. So originally, what you have in the left side is just y squared minus 2y. I want to make it a perfect square. That way, it would look like this. Okay? So what is it in your algebra that you've learned how to make a particular expression a perfect square? So what you do, you divide this number here, the number that you see on the y, the coefficient of y by 2, and you square it. That should be the number that you should add to it. Y, come to check. Y squared minus 2y plus 1 is actually equivalent to y minus 1 squared, which is a perfect square. If you'll expand this one, it will be equivalent to this. Y squared minus 2y plus 1. Now, hindi man pwede nga kung diri nagdugang ika 1, you will not add 1 on the other side because you will be changing the original solution because your original solution is only this. So since you altered the left side by adding 1, you also add 1 on the right side. That way, you did not alter the original form of the solution. So this is it, class. You add 1 here, you also added 1 here. Now what happens is this one and this arbitrary constant, just like the 3c that was asked a while ago, will be combined to represent another arbitrary constant a. Or you can even still write it as c, it doesn't matter. Okay, just for illustration purposes, this a is already the sum of 1 and c. Okay, so this one, this particular equation is no different than the last equation you have seen in the previous page. Now, after that, since this is squared, you take the square root of both sides of this one. So you take the square root of x cubed plus 2x squared plus 2x plus 8. And it should be plus minus because when we take the square root, it could be either a positive or a negative root. Okay? This one will be left with y minus 1. Now, you want it explicitly written, meaning as what I have said a while ago, I should only see the unknown function here, the y, on the left side. The rest of the expression should be written on the right side. So you see it like this. You transfer the 1 here by addition on the right side. And this is now what we call as the explicit solution. So from implicit in the previous page, you have converted it to an explicit solution. Question: Miss, is there a need for us to always present our final answer in explicit form? The answer is no. If the quiz is open-ended wherein you are to show your solution, and if it's not indicated in the instruction that you are to write in explicit form, this answer or the answer in the previous page will already do. No need to write it in explicit form. In cases wherein you are provided with choices and your answer, the answer that you got, you can't find among the choices, meaning it could be only any of the 3 scenarios. Your answer is wrong, your answer was not simplified, or your answer needs to be converted in explicit form. So if you are confident that your answer is correct, then convert it in explicit form or simplify it. That way you'll find it among the choices. And that's the downside of having multiple choice, because you always have to make sure that your final answer is simplified. Okay? Now, before I go to the next slide, is there any question in this part? Okay, so thank you anyway. I'm happy that you know you're completing the square from algebra in converting from implicit to explicit form of the solution. So let's go to the next. Now, if you are given an initial value problem or a differential equation in which there is an initial condition, I will use the annotation here. This is the initial condition. What if in the previous example, example number 2, you are given the condition that when x is equal to 0, this one is for the x, y is equal to -1. What will you do? Your answer need not be explicit, class. Your answer, in whatever form it may be, it may not be even simplified yet, you substitute the values of the variables here. So for y, you need to substitute -1. For x, you need to substitute 0. So all of this will be gone, giving you a C value, which is 3. Okay, this is your 3. Thus, the implicit equation defining y is now y squared minus 2y equal to x cubed plus 2x squared plus 2x plus 3. Okay? Using explicit expression, on the other hand, kung gamiton, tanay ang na-explicit kaina just before this page. Anyway, that's x plus minus this one. Or rather, 1 plus minus this one. You just substitute right and then the value of y, -1, and x equal to 0 to the same expression that you got. And you'll be getting a constant, which is C sub 1 or C or A, whatever that will be. And then your solution would be like this also. So if I may say, your solution would either be in this form, your particular solution could be in this form, or it could be in this form, depending on where you substituted the initial condition. Okay? So normally, class, when I give a problem wherein you are to determine the particular solution, because this one is particular, doesn't have any arbitrary constant, I will specify whether you are to first express it in explicit or an implicit solution will do. So you need not worry, but any of these 2 solutions are acceptable. Okay, now I would like to end here. You see these curves here that you see on the right side, and you see this black thing in here, the black curve in here. This is the curve represented by this particular explicit solution. This one. Why, miss? Because I used the minus sign, or what was used here is the minus sign. What if it's the plus sign? We'll clear all the drawings. What if it's the plus sign? You will have a different curve. The plus sign is this one. the curve above the horizontal axis. So this explains, class, this explains why we have what we call in differential equations family of solutions. Because your solution, specifically your particular solution, when graphed already for a particular differential equation will be dependent on the condition that is given together with the DE. If the condition is changed, the corresponding curve will change also. But take note, the shape of the curves are all the same. They will just differ in terms of size, but the shape is just the same. So we say they belong to the same family of curves, representing the family of solutions to a particular differential equation. In the first place, class, if we'll stick to this one, if we will stick to this particular answer, the implicit general solution or the explicit general solution, where is that explicit general solution? This one. You have the presence of the C. The C alone will be any value. So it can have any infinite value. So as such, you will have different curves for that. But the shape, as I said, will be the same. So that is why we call it a family of solutions. Okay? So my class is very attentive this afternoon. So we have finished 2 topics in just 1 hour. Now, this one, I leave for you to read, just like what I did with my other classes. Okay? You read because what you're going to do here is also separate variables. Anyway, I have here outlined, I have already outlined the solution. My practice class is this ever since, even if it's not pandemic, what I do, since there are several topics under first order DE, after 3 topics, so after separable DE, we'll be discussing homogeneous, and then after that, we'll be discussing exact. After the first 3 topics, that's the time that I will give you added solve problems on these particular topics after. Why would I do that? Because I want you to practice first on your own. I don't want you to rely on me to give you so many solved problems. When I'm already confident that you have done your thing, then I will give you more sample problems, but after 3 topics only. So if you're given here problem sets to solve, make sure that you do make use of the collaborative learning process. What do I mean with the collaborative learning process? You will have to group yourselves. I will post in the announcement later on how you're going to group yourselves, and you will accomplish the problem sets that were assigned to be accomplished by group as a group. So meaning you assign a particular problem for one person to answer, another person, another problem, and then you share your solutions. That way, you get to have what we call the meeting of minds, collaboration in learning. There are assignments that will be done individually, but most of the problem sets are done by group, and you will only be submitting one solution for the group. And the point for that will be similar or will be the same for all those that are members of the same group. Okay, so this is the last part of the slide on that particular sample problem. Okay, I will be sharing all the recordings of the lectures here to you, just like what I did with my other 3 classes. So just wait for it to be also shared to you in Canvas. You will see it under lesson. So lesson, and then you will have lesson recordings. That way you can go back to what we have discussed and listen again. Okay, I will stop sharing. And it's 5:30 on the dot. Do you have any questions? I can entertain questions if you want to ask questions.
Ang PPT yung Miss Ara, punta sa kanila.